Basic Mechanical Drives, Part 2. This is based largely on a presentation from SlideShare by James Shearer, but it was adapted, added to and presented by me, Jean Leguet. Here's the legal stuff. So this is part of a series of videos looking at drives. We're going to be looking at geared drives. A gearbox is used to provide a variable output speed from a constant speed power source, or to provide torque increase for a variable speed power source. Geared transmission provide only specific fixed speed ratios. They're durable, rugged and efficient, but are capable of only providing a specific number of fixed gear ratios, normally chosen for applications involving heavy load or requiring long, trouble-free life. Generally more expensive than belt or chain drives, gear drives are commonly classified according to their end use. Automotive transmissions are used as the main transmission in cars, trucks, farm machinery, earth-moving machinery. It can either be automatic transmission or manual transmission, or the halfway house, which is the double clutch transmission. They usually provide from 4 to 10 speeds. Auxiliary transmission is usually installed behind the main transmission to increase available ratios. Sometimes this was called overdrive. Transfer cases. These provide additional power outlets, such as for the extra two wheels in a four-wheel drive, or provide offsets from normal drive lines. Power takeoffs. These are usually mounted beside the main transmission and driven by an additional gear. These are often used in agricultural systems to provide power to machinery. Marine gears. Transmission carrying power to the propeller on a marine drive. These differ from other transmissions in that they generally provide single forward and reverse speeds and use a friction-type shifting clutch. Hydraulic drives. Gearboxes connecting power sources and hydraulic pumps in hydrostatic drives. Industrial transmission. This is a broad category applying to any transmission powering machinery other than that described above. Many have integrated power packages, such as electric or hydraulic motors, or they may be an integral part of a driven component. A differential. This is a set of gears with three independent rotating members with a speed and torque component. What this allows is for one input and two outputs, and for the outputs to go at different speed while still providing torque. The automotive differential is the best example. The second application type has two inputs and one output. Less well known than the first, this technique solves industrial problems when the superimposition of one motion relative to another is required, such as timing of cutoff, registration control on printing presses, tension control, and phase shifting on textile industry equipment. A mechanical fixed-speed drive offers the best combination of rugged and reliable speed reduction at low cost. Any single factor, such as the lubrication needed for chains or the durability and slip on belts, sets the mechanical gearbox apart as the clear choice for most applications. A gearbox may have one or more gear pairs. The gear pairs may be on parallel or non-parallel axes and on intersecting or non-intersecting shafts. If it has more than two pairs, the setup is called a gear train. Generally, they permit high speed ratios in smaller packages than are feasible with a single pair of gears. Series trains. Overall ratio is input shaft speed divided by output speed. It's also the ratio of the individual mesh, except on planetary gears. Ratio is most easily found by dividing the number of teeth of the driven gears by the product of the number of teeth of the driving gears. Planetary gearing, also called epicyclic gearing. It is a gear train in which the planet gear rotates on its own axis, while its axis rotates about another gear called the sun gear. Speed reducers. Gearboxes usually offer only a single fixed ratio reduction. As the name implies, a reducer is almost always used to gear down. Speed increases. These gearboxes require special care in design and manufacturing. They often involve high speed, which may create problems in gear dynamics. Also, frictional and drag forces are multiplied by the gear ratio. So a gear is basically a wheel with slots cut in it. Here's an example of a fork type direct torque DTC right angle conveyor drive. It has helical and spiral bevel gears. We'll be looking at those later. Spur gear might be called the basic gear, since all the other types have been developed from it. Its teeth are straight and parallel to the center bore line, as shown above. Spur gears may run together with other spur gears or parallel shafts with internal gears on parallel shafts, and with a rack. A rack, such as one illustrated, is in effect a straight line gear. The smallest of a pair of gears is often called a pinion. The involute profile, or form, is the one most commonly used for gear teeth. It's a curve that is traced by a point on the end of a taut line unwinding from a circle. The larger the circle, the straighter the curvature, and for a rack, which is essentially a section of an infinitely large gear, the form is straight or flat. The generation of an involute curve is shown in the next slide. The involute system of spur gearing is based on a rack having straight or flat sides. All gears made to run correctly with this rack will run with each other. The shafts are in the same plane and parallel. The teeth are cut straight and parallel to the axis of the shaft. No more than 2 sets of teeth are in mesh at any one time, so the load is transferred from one tooth to the next tooth rapidly. Usually spur gears are used for moderate to low speed applications. Rotation of spur gear sets in opposite unless one or more idler gear are included in the gearbox. Typically spur gear sets will generate a radial load opposite the mesh on their shaft support bearings and little or no axial load. We use the word involute because the contour of gear teeth curve inward and is used in gear tooth profiles. The involute curve is a curve that is traced by a point on the end of a taut line unwinding from a circle. The larger the circle, the straighter the curvature. You attach a string to a point on a curve. Extend the string so that it is tangent to the curve at the point of attachment. Then wind the string up, or unwind it, keeping it always taut. The locus of point traced out by the end of the string is called the involute of the original curve, and the original curve is called the evolute of the involute. The process is illustrated above. Here it is just again. The size of each tooth inclined towards the center top at an angle called the pressure angle. The 14.5 degree pressure angle was standard for many years. In recent years, however, the use of the 20 degree pressure angle has been growing, and today 14.5 degree gearing is generally limited to replacement work. The principal reasons are that the 20 degree pressure angle results in a gear tooth with greater strength and wear resistance, and permits the use of pinions with fewer teeth. It's extremely important that the pressure angle be known when the gears are mated, as all gears that run together must have the same pressure angle. The pressure angle of a gear is the angle between the line of action and the line tangent to the pitch circles of mating gears. Pitch circles have been defined as the imaginary circle that are connected when two standard gears are in correct mesh. The diameter of these circles are the pitch diameter of the gears. The center distance of the two gears, therefore, when correctly meshed, is equal to 1/2 of the sum of the two pitch diameters. This relationship may also be stated in an equation and may be simplified by using letters to indicate the various values. A specific type of pitch designates the size and proportion of gear teeth. In gearing terms, there are two specific types of pitch: circular pitch and diametrical pitch. Circular pitch is simply the distance from a point on one tooth to a corresponding point on the next tooth, measured along the pitch line or circle. Large diameter gears are frequently made to circular pitch dimensions. The diametrical pitch system is the most widely used, and practically all size gears are made to diametrical pitch dimensions. It designates the size and proportion of gear teeth by specifying the number of teeth in a gear for each inch of the gear's pitch diameter. It's most common to still use inches when calculating gear pitch. For each inch of pitch diameter, there are pi inches, or 3.1416 inches of pitch circle circumference. The diametric pitch number also designates the number of teeth for each 3.1416 inches of pitch circle circumference. Stated in another way, the diametrical pitch number specifies the number of teeth in 3.1416 inches along the pitch line of a gear. Because the pitch line of a rack is a straight line, a measurement can easily be made along it. The slide illustrates that there are 10 teeth in 3.1416 inches. Therefore, the rack illustrated is a 10 diametrical pitch rack. In most cases, particularly on machine repair work, it's desirable for the mechanic to determine the diametrical pitch of a gear. This can be done very easily without the use of precision measuring tools, templates or gauges. Measurements need not be too exact because the diametrical pitch numbers are usually whole numbers, because there's a whole number of teeth on a gear. Therefore, if an approximate calculation results in a value close to a whole number, the whole number is the diametrical pitch number of the gear. A simple method is to count the number of teeth in the gear, add 2, and divide by the outside diameter of the gear, and then scale it to the nearest whole number. Here's just some of the names used to name various parts of gears. The addendum. This is the distance the tooth projects above or outside the pitch line. The dedendum. This is the depth of tooth below the pitch line. Clearance. This is the amount by which the dedendum of a gear tooth exceeds the addendum of the matching gear tooth. Hole depth. This is the total height of a tooth or the total depth of the tooth space. Working depth. This is the depth of tool engagement of two matching gears. It is the sum of the addendums. Tooth thickness. This is the distance along the pitch line from one side of the gear tooth to the other. Backlash. This is the play in the system. Basically, when you reverse a system, the distance that you travel between the driven component and the driving component before the driven component actually starts to be driven is backlash. In terms of tooth dimensions, it's the amount by which the width of a tooth space exceeds the thickness of the mating gear. It can be described as the distance, measured along the pitch line, that a gear will move when engaged with another gear that is fixed. Normally, there may be some backlash present in gear drives to provide running clearances. This stops binding that could result in heat generation, noise, abnormal wear, or possible overload. A small amount of backlash is desirable because of the dimensional variations involved in manufacturing tolerances. Backlash is built into standard gears during manufacturing. On non-reversing drives or drives with continuous load in one direction, the increase in backlash that results from tooth wear does not adversely affect operation. However, on reversing drives and drives where timing is critical, excessive backlash is usually not tolerated. Many styles and design of gears have been developed from the spur gear. While they are all commonly used in industry, many are complex in design and manufacturing. Only a general description and explanation of principles will be given, as the field of specialized gearing is beyond the scope of this presentation. Commonly used styles will be discussed sufficiently to provide the millwright or mechanic with the basic information necessary to perform installation and maintenance work. Two major differences between bevel gears and spur gears are their shape and the relationship of the shafts on which they are mounted. The shape of a spur gear is generally a cylinder, while the shape of a bevel gear is a cone. Spur gears are used to transmit motion between parallel shafts, while bevel gears transmit motion between angular or intersecting shafts. Special bevel gears can be manufactured to operate at any desired shaft angle. Mitre gears are bevel gears with the same number of teeth in both gears, operating on shafts at right angles. The diametrical pitch number, as with spur gears, establishes the tooth size of bevel gears. Because the tooth size varies along its length, it must be measured at a given point. This point is the outside part of the gear where the teeth are largest. Because each gear in a set of bevel gears must have the same angle and tooth lengths as well as the same diametrical pitch, they are manufactured and distributed only in mating pairs. Bevel gears, like spur gears, are manufactured in both the 14.5 degree and 20 degree pressure angle design. Helical gears are designed for parallel shaft operations, like the pair shown. They are similar to spur gears, except that the teeth are cut at an angle to the center line. The principal advantage of this design is the quiet, smooth action that results from the sliding contact of the meshing teeth. A disadvantage, however, is higher friction and wear that accompanies the sliding action. The angle at which the gear teeth are cut is called the helix angle. The shafts are in the same plane and parallel, but the teeth are cut at an angle to the center line of the shafts. Helical teeth have an increased length of contact, run more quietly, and have a greater strength and capacity than spur gears. Normally, the angle created by a line through the center of the tooth and the line parallel to the shaft axis is 45 degrees. However, other angles may be found in machinery. Helical gears also have a preload by design. The critical force to be considered, however, is the thrust load, axial load, generated in normal operation. The worm and worm gear are used to transmit motion and power when a high ratio speed reduction is required. They provide steady, quiet transmission of power between shafts at right angles. The worm is always the driver, and the worm gear the driven member. The worm gear cannot drive the worm. Like helical gears, worms and worm gears have hand. The hand is determined by the direction of the angle of the teeth. Thus, in order for the worm and worm gear to mesh correctly, they must be the same hand. That means right-handed or left-handed. The herringbone gear. Interesting fact, this was largely developed by André Citroën, hence it's used as a symbol of Citroën cars. It overcomes the disadvantage of high-end thrust present in helical gears. The herringbone gear consists of effectively two helical gears with different hands attached together. The gear teeth of both hands cause the thrust of one set to cancel out the thrust of the other. Thus the advantage of helical gears is obtained and quiet, smooth operation at higher speeds is possible. Obviously they can be used for transmitting power between parallel shafts. They're commonly called double helical because they have teeth cut with right and left hand helix angles. They're used for heavy loads at medium to high speeds. They do not have the inherent thrust forces that are present in helical gears. Herringbone gears, by design, cancel the axial loads associated with a single helical gear. Many machine trains utilize gear drive assemblies to connect the driver to the primary machine. Gears and gearboxes typically have several vibration spectra associated with normal operation. Characterization of a gearbox's vibration signature is difficult to acquire, but is an invaluable tool for diagnosing machine train problems. All gear sets create a frequency component called gear mesh. The fundamental gear mesh frequency is equal to the number of gear teeth times the running speed of the shaft. In addition, all gear sets will create a series of sidebands or modulations that will be visible on both sides of the primary gear mesh frequency. In a normal gear set, each of the sidebands will be spaced at exactly 1 times, 2 times, 3 times, etc. the running speed of the shaft, and the profile of the entire gear mesh will be symmetrical. The sidebands will always occur in pairs, one below and one above the gear mesh frequency. The amplitude of each of these pairs should be identical. Any asymmetry in the frequency is an indication of wear or some type of abnormality in the gear train. One of the primary causes of gear failure is the fact that, with few exceptions, gear sets are designed for operation in one direction only. Failure is often caused by inappropriate bidirectional operation of the gearbox or backward installation of a gear set. Unless specifically manufactured for bidirectional operation, the non-power side of a gear teeth is not finished. Therefore, this side is rougher and does not provide the same tolerance as the finished power side. Gear overload is another leading cause of failure. In some instances, the overload is constant, which is an indication that the gearbox is not suitable for the application. In other cases, the overload is intermittent and only occurs when the speed changes or when specific production demands cause a momentary spike in the torsional load requirement of the gearbox. Misalignment, both real and induced, is also a primary root cause of gear failure. The only way to assure that gears are properly aligned is to hard blue the gears immediately following installation. After the gears have run for a short time, their wear pattern should be visually inspected. If the pattern does not conform to vendor specification, alignment should be adjusted. Poor maintenance practices are the primary source of real misalignment problems. Proper alignment of gear sets, especially large ones, is not an easy task. Gearbox manufacturers do not provide an easy, positive means to assure that shafts are parallel and that the proper center-to-center distance is maintained. Induced misalignment is also a common problem with gear drives. Most gearboxes are used to drive other system components, such as bridles or process rolls. If misalignment is present in the driven member, it also will directly affect the gears. The change in load zone caused by the misaligned drive component will induce misalignment in the gear set. The effect is identical to real misalignment within the gearbox, or between the gearbox and mated components. Visual inspection of gears provides a positive means to isolate the potential root cause of gear damage or failure. The wear pattern, or deformation of gear teeth, provides clues as to the most likely forcing function or cause. The first picture illustrates a gear that has a normal wear pattern. The entire surface of each tooth is uniformly smooth above and below the pitch line. Abrasion creates unique wear patterns in the teeth. The pattern varies depending on the type of abrasion and its specific forcing function. The second picture illustrates severe abrasive wear caused by particulates in the lubricating oil. Note the score marks that run from the root to the tip of the gear teeth. Water and other foreign substances in the lubricating oil cause gear degradation and premature failure. The first picture illustrates a typical wear pattern on gears caused by water. The wear pattern generated by excessive gear loading vary, but all share similar components. The second picture illustrates pitting caused by excessive torsional loading. The pits are created by the imposing of lubricating oil. Cavitation, in other words. Other wear patterns, such as scalding and burning, can also help to identify specific forcing functions or root causes of gear failure. And that's the end of part 2.